Good morning, dear participant. We had two lectures. One is on overview of Earth observation for carbon cycle assessment. The next, mainly focusing on measurement, instrumentation, and certain observational network which support measurement of ecosystem exchange between biosphere and atmosphere. Apart from this observational network, because observation network is existing across the globe, but we cannot have, or developing countries cannot afford to have a dense observational network to support spatially explicit information on carbon exchange or carbon budget. Observation can serve as a sites, or observations can serve as a database to constrain certain kind of technique, remote sensing or certain model. So over the period of time, there is a large scale development with respect to the simulation modeling is categorized into different kind of models. So these are not different simulation models, whether it is physically based, simple deterministic model, or stochastic model, or machine learning based model. Different kind of model have been developed with the database observational network along with the supportive observation either from satellite or from meteorological observation network. So both meteorology, remote sensing serve as a independent or certain causal variables, and observational site they are now serving as a basic reference sites for developing certain kind of models. So now we'll see how this observation available from different sensor, how they can be used for upscaling and modeling with the different kind of model. So if you see the strength of the observational network, there are different kind of satellite available, which are operative in the optical, thermal, microwave, both passive and active, as well as certain LIDAR, and then there is also sun-induced fluorescence observation now available. So different kind of techniques are there: thermal, reflective, optical, emitted energy, reflective energy, as well as microwave, base scatter, brightness, temperature. All different product or parameter derived from different kind of satellite are being used for modeling carbon fluxes as well as terrestrial productivity. So there are different kind of satellite, like ranging with the different kind of resolution from 1 meter to almost 1 kilometer partial resolution, and temporal resolution also from half hourly data available to up to almost once in a month. So there are certain sensors like IIRS or QuickBird, which are having a resolution less than 1 meter. So sometimes a question arises in our mind where it can be used. This kind of is very much useful with respect to the carbon footprint. Suppose you want to estimate which are the different kind of cropping system or crop fields which are carbon sink. If you want to identify the carbon storage for field parcel level, then this kind of IIRS, QuickBird, this kind of satellite that can help you to geotag fields as well as demarcate field boundary and delineate that which are the different kind of crops are there. Then after you apply certain kind of IPCC procedure or certain procedure to evaluate carbon emission for field wise. That is more or less you can say observational and inventory based database you can create with the high resolution data. But there are also like spot vegetation or coarse resolution satellite data like Terra Modis, NVSat, radar sensor like IIRS, NVSat. All those are also very much useful for the some kind of observation on the atmosphere. Some parameter Landsat and NOAA, they are very good for hydrology, land cover, vegetation dynamics. So all those satellites, whether available from advanced sweeps, IIRS satellites, or NASA Terra satellites, or you can say European Space Agency, IIRS, or you can say any microwave related satellite, all has got tremendous potential to address various kind of parameters which are required for the terrestrial primary productivity modeling or vegetation cover change or forest fire. Because finally, to evaluate carbon, we need to have first productivity, gross primary productivity. Then we need also soil respiration, which is a function of soil moisture. So we require some soil moisture information from satellite also. Then also there is a heat require land use land cover change, crop harvest, forest fire as a disturbance design. So all satellite has got one or another way playing a role to evaluate carbon footprint of different managed or natural ecosystem. So there are different kind of wavelength which has been used for the different purpose. Mainly satellite remote sensing that works with the blue visible wavelength, then near infrared, then middle infrared, thermal infrared, then microwave. So microwave, that is both active and passive. There are active sensor like IIRS, radar set, then our reset, all are, and then future plan is NISAR, boosting the synthetic aperture radar with the S and L band. So these all satellites which are having some kind of microwave sensor, synthetic aperture radar, that can also help you to detect biomass, because they have more penetration capability to acquire information about canopy structure. So certain satellite which are having ability with different kind of polarimetry, they can able to derive canopy structure and biomass. That is why, and also you can derive different kind of crop species also, particularly whenever there is a cloudy weather. Thermal data, that is a radiometer, infrared radiometer, which is available on IIRS, MODIS, as well as Landsat. All data having a thermal band. Thermal band is a vital information which is very much critical to evaluate, derive land surface temperature and evapotranspiration. And evapotranspiration, as I said earlier, it is closely linked to the photosynthesis. Both are reciprocal process. So evapotranspiration stress, that also regulate the how much carbon is uptake by the vegetation. So we need to take thermal infrared information, which is very critical to determine different kind of water stress or environmental stress on the primary productivity. Middle infrared, there is also a land surface wetness indices one can generate to evaluate as a water stress condition to a limiting condition of the photosynthetic efficiency as well as primary productivity. Particular visible red and near infrared, they are very much useful mainly for the vegetation index retrieval, albedo, vegetation density, and also it can be very much useful for the land use land cover. So all this info data, which is very much vital, are useful for deriving one or another parameter of which is very much critical to derive primary productivity or carbon fluxes. Now we look into the upscaling, because we have to think about observation are now available globally. Yesterday I have shown there are almost 900 sites of eddy core flux tower. Many people have tried to develop a certain kind of upscaling or data mining technique or machine learning based approach to partially derive this different kind of variable fluxes. But so scaling theory mainly provide importance clue towards understanding and modeling space-time variation or dynamics of different biophysical processes. Because observation are good, they are very much continuous observation over time, but they are discrete. They are not uniformly distributed, or they are very much sparse. So with the kind of remote sensing, integrating remote sensing or certain kind of upscaling technique, we provide partially explicit variability of the biophysical process at the land surface or ecological process or vegetation dynamics. So these land surface process means whether it is an exchange of mass, momentum, water vapor, or any entity from biosphere to the atmosphere that range from the small field size, small patch like one single field to the global. Because from single field, by observation or by taking photosynthetic meter observation and upscaling to canopy scale, you can measure for field scale processes. From field scale to landscape, then landscape to almost region, then region to global. This is a called upscaling process. For at different stages, you require different sort of database for either for remote sensing, satellite, or meteorological variable, or for meteorological observatory. So both meteorology and the remote sensing data serve as a variable, for the upscaling that observation from the different flux site. So this also very useful to achieve if produced flux or rates are very linearly related. Because why upscaling came into existence? Because all processes, or whether photosynthesis, yesterday we have seen there is a mycelium minant function, and there is a nighttime temperature against the nighttime respiration against the temperature. There we have seen there is a non-linear relationship. After certain threshold of photosynthetically active radiation, GPP gets saturated. So it is a non-linear response. If linear is there, if there is no issue of upscaling, you can directly extrapolate and you can get. But these are all biophysical processes which are non-linear in nature. So very difficult to upscale. So linearly related, then okay, you can simply apply certain kind of statistical technique, linear variable, develop linear relationship, regression relationship between one variable with another variable, and then we simply apply. It works. But the moment there is a non-linearity exists in the biophysical processes, what you are measuring, then you have to take into account certain kind of non-linear parameterization or non-linear equation. So most of these upscale new models based on the machine learning based models like random forest or support vector machine or artificial neural network or deep neural network or deep learning or machine learning, different algorithms people are being testing. So those all are addressing the non-linear response. So this all non-linear response, if it is involved, then we have to do certain kind of machine learning techniques through upscaling. So upscaling, why required? Because it makes a significant challenge in non-linearity between processes and variable and partial heterogeneity in surface and atmospheric properties. Because then when there is non-linearity, we cannot simply extrapolate. Secondly, when there is a high degree of partial heterogeneity, because as I said, we cannot afford to have dense network. We cannot install 500 tower in India because it is very much huge cost involved. We have to take into account cost benefit ratio also. So we cannot measurement are very good, but they can be used for constraining certain kind of model, and then finally we use those kind of model to upscale to a whole nation level. So this is a one way of doing upscaling. There 80 flux tower which provide observation from almost 100 meter to 1 kilometer footprint, and it has got temporal interval from hour to almost annual. Or some, yesterday I have shown you there are certain sites in USA which are having almost 20 years of data. So you can do nowadays 80 flux tower up to 20 years from single day to up to 20 years data, historical on daily time scale data is available for certain station. That is why partial scale it has got footprint up to 1 kilometer. So suppose you want to do beyond 1 kilometer, like whole Uttarakhand or whole Indo-Gangetic plain or whole India, then we have 329 million hectare land mass. with a different kind of forest type, grassland, savanna, ecosystem, then rock outcrop, and then barren and urban. So many kind of land use is there. If we address all this, then we may require so many towers. So representative even we do, at least we cannot do, because with such a high spatial heterogeneity in the land use land cover. So this AD plus tower, wherever it is located, we can use together with the certain kind of satellite data. Here we have, I kept only Modi's, but there are different kind of data like spot vegetation, our Indian remote sensing satellite, advanced sweeps, then also insect data, different kind of geostationary satellite as well as remote sensing satellite data, which has got the daily repeat cycle or the 10-day composite that can be used along with the plus tower observation from different site to upscale through certain kind of machine learning models. We can finally derive this grid scale map of the GPP. Grid scale means partially explicit information of the GPP, NEP, or the ecosystem respiration. So that is also weak to 20 years, and we can derive up to almost global. If we use global database, FluxNet site on 900 site, and take satellite observation and develop certain kind of automatic machine learning models, random forest or something, we can upscale and prepare global map of these different carbon fluxes. So this is one approach where suppose this is one small site, one tree is there, you can take some photosynthesis measurements, certain other biophysical property, leaf area index, and then that photosynthesis you can do scaling with the Facrular model, and you can compute certain kind of at canopy scale photosynthesis. Then in a particular landscape of 1 by 1 kilometer, there is a one tower. Next stage is a 1 by 1 kilometer. So there that not much detailed observation required. You have tower, you have certain feet, where a plot, you demarcate certain plot and take certain measurement and make canopy scale or landscape scale, that is 1 by 1 kilometer fluxes. Then those again one region is there, suppose 100 by 100 kilometer, which is having 4 or 5 tower, 4 or 5 vegetation types representing with the different kind of tower. Then you use those tower along with the remote sensing and certain ecosystem model. Further you can extrapolate to the region like Indo-Gangetic Plain or peninsular region. Then from that further you go to the global or continent. So it is a step-by-step process from one plot to the landscape to the small region to the region and then global and continent. That way, depending upon the data, because in initial scale you require very high resolution data like Pickford or Iconos, that kind of data. Next stage you may require least 3 or that Landsat kind of state data. Third stage you require certain kind of or even second stage you require UAV or that other kind of thing also. Third stage you may require some MODIS or that kind of data. Further you require sun-induced fluorescence half degree data, half degree or certain quarter 0.1 degree vegetation index. You can do some global scale modeling. So this way, how upscaling can be done from the simple flux tower or some in situ measurement to the landscape, to the region, and then to the finally globe. So here, one model is there, that is a temperature Guinness model. Temperature Guinness model, it has capability to address both moisture stress and the temperature stress in the biospheric exchange of the carbon. So temperature means land surface temperature, greenness means enhanced vegetation index. Both are scaled like you can scale LST between minimum to maximum. Beyond 50 there is no photosynthesis, beyond 0 there is no photosynthesis, and between 0 to 50 there is a photosynthesis. So here you can see that for one tower site we have identified optimum temperature for the wheat a wheat gross photosynthesis against the land surface temperature. Optimum temperature is 30 degrees centigrade. So both 30, less than 30 and above 30, it will decline GPP, it will limiting GPP, and at the 30 degrees centigrade, it will be a peak. So based on this scaling, and then also EVI you can scale, take multiple of the scale EVI and scale LST, one can get GPP. So you can see this is okay, one TG model for wheat crop. We have evaluated in somewhere, okay, past, it is published somewhere. So you can see this, okay, there's a linear relationship where, okay, scaling coefficient we derive 4.32 mole per carbon per meter square per day against GPP for the wheat crop. This M factor that varies from biome to biome. So if we take some sigmoidal growth curve, it is better even fitted to the this TG model. Same TG model you can derive with the even hyperspectral data. We have tried already certain kind of different relations with the PAR multiply with the photochemical reflecting index or enhanced vegetation index or certain, okay, chlorophyll related index. It is giving direct relationship with the net photosynthesis. So what I want to say that if instead of only the one NDVI or enhanced vegetation index, if you are having a certain measurement which gives you information about like sun induced fluorescence, or if you are having a photochemical reflectors index, that is PRI, which is highly sensitive to the photosynthetic efficiency because it is closely related with the photosynthesis and it is better estimate of LEV. So if you take that PRI along with the PAR and some certain vegetation based indices, it gives better relationship with the gross primary productivity. So initially we have to see the response. These are the different effective remotely sensed variable that can be used in deriving in the training for the developing upscaling model. So this is okay. Another, okay, for the forest site, one is a barcode and another is a mixed plantation, and one is a dry deciduous barcode site. Now same TG model here we have applied, and you see the M factor in the mole for this, okay, particularly for the not M factor is varying between these two. And then if we have done this with the relation with the temperature, precipitation, and water limit, water content, LAI, different relationship is there for the moist deciduous and dry deciduous. But there is a significant relation between the TG model against the tower-based observation. So using this, we have generated last 20 years of database for the GPP over these two, Haldwani subdivision and the barcode subdivision. It is well agreed with the tower observation. So this kind of scaling, upscaling you can do with this, okay, like this, okay, TG model, some models we have validated with Haldwani mixed plantation and also the barcode forest site. Here, that whole based on the relationship, we have worked out map of the GPP for the barcode division. Then this is for GPP for the Haldwani subdivision. So based on this MODIS data or Landsat data available, because here for barcode division it was mainly with the MODIS data, that is why it looks pixelated, the coarse resolution. Haldwani it is mainly with the Landsat, but monthly wages with high resolution GPP. So that was all about, okay, simple relationship and applying it to the with the observation, which little, many, very scanty observation, whatever available in India, because we don't have, okay, very large network of the flux tower site across India. Hardly now it is growing. We have, okay, some ISRO has set up some 10 to 12 towers are there, and then some tropical Institute of Tropical Meteorology, Ministry of Earth Science, and then ICR. Together, okay, we are now representing, okay, certain biome types. Still, okay, Western India and certain part of, okay, Southern India. Still, okay, network is scanty. Yes, yesterday I showed some map also about where different sites are there. So if we have certain more around 32 equally distributed across India, then we can take up this certain kind of upscaling technique with the satellite based remote sensing for the estimating carbon fluxes. Now this is not only this you require tower based observation. Even if you are having a certain kind of plot observation, plot based biomass sampling, or you can soil organic carbon sampling, wall to wall mapping, that also you can upscale with the satellite based observation, whether it is a lidar or SAR based, or you can say certain simple indices, vegetation indices. You can relate, and further you can upscale this plot based biomass or plot based soil organic carbon or plot based ground density to the landscape level, and further with the high result with the global continent level. And you can able to identify how biomass changes is taking place over a period of 10 years, 15 years, to identify what spot of the deforestation. So rate of deforestation or rate of carbon emission from the forest through forest inventory database on regional and national scale can be possible with the plot laying out of thousands of plot, because in our tomorrow you will see, have a glimpses about the how this sampling approach can be implemented for the vegetation carbon biomass assessment across India under vegetation carbon pool. Thousands of plots were laid out by tomorrow. Our lecturer Dr. Sanam Singh will explain you in detail. So now that was all simple relationship and certain kind of statistical relationship of, that can be useful for the upscaling. But apart from this, nowadays modeling, whether it is a simple model like based on simple relationship of precipitation and temperature with the MPP or GPP, also to the very sophisticated biogeochemical model or dynamic vegetation model. So there are different kind of models which are being used. Some are static, some are dynamic. Static model like yesterday we have shown land use efficiency. Land use efficiency based model are static model, but there are more some process based model are also static model. But there are models which has been developed, which are mainly specifically climate driven model, are called dynamic vegetation model. So which takes into account the simulation of the structure and composition of the particular surface, land surface. So you can simulate how these different kind of biomes will vary over a period of time in the future climate. So those kind of dynamic vegetation models are very much useful for studying effect of climate change in the future. How this biome distribution will take place, how those changes in the biome will affect this carbon fluxes, and further how it will lead to the changes in the final climate change and its impact on the productivity as well as other related aspects and biogeochemical processes. So biogeochemical models, they simply have a because most of this, whether it is efficiency based model, process based model, or dynamic global vegetation model, when we are talking about the ecosystem functioning, then they are mainly the biogeochemical model. So biogeochemical model simulate functioning of terrestrial ecosystem in terms of carbon fluxes, whether it is gross primary productivity, NPP and NEP, and evaluate effect of environmental changes. So those biogeochemical models are called canopy-based model, that is nothing but efficiency-based model. So it is evaluating terrestrial GPP and NPP as a function of land cover, radiation interception, and environmental stress. So there are different kinds of models available globally implemented with the satellite data are global PM model, CFIX, Cambridge, and Stanford approach, CASA, Modi's algorithm, vegetation photosynthesis model, all are directly amenable to the satellite observation. Second category of ecosystem models are terrestrial ecosystem models. These are mainly the process oriented, means they are climate driven and mainly the process oriented. They simulate on a daily time step or sometimes even hourly, like okay, particularly dynamic vegetation model, some certain land surface model which gives an hourly fluxes. So process oriented and simulate exchange of carbon, water and nutrients, mainly nitrogen also, between atmosphere and terrestrial biosphere on regional and global scale. So they are mainly regional scale. They are not directly related, amenable with satellite observation because they are driven by climate, and we don't have right now climatology or historical climate available at very high partially grid resolution. Whole global it is available right now at 0.5 half degree. India we have temperature, climate temperature on monthly time scale or rainfall on monthly time scale available at 0.25 degree grid scale. So those, because all those model, if you want to run for the region or global, it require partially gridded data set, not only point data set, one place. So it requires gridded data set. So these are the all global or regional scale model implemented with the post resolution gridded climate data set. NPP, that is a GP, mainly as I said earlier, GPP minus RA, autotropic respiration, and NEP, net ecosystem productivity or net ecosystem carbon exchange, equal to NPP minus heterotropic respiration. NPP, GPP, and respiration all are estimated at different level of complexity because it depends on the how good observation you have. It depends on the what is the correctness of the algorithm you are using, or assimilation of observation or assimilation of satellite data into a certain kind of model, all influence the model. And different models are there with the different complexity, because certain are models that only use temperature based equation, certain model use land cover, temperature and soil moisture based equation for the ecosystem respiration. So there are different degree of complexity also. So yesterday already I shown all these things. But land cover classification you can derive from remote sensing. Phenology, mainly phenology means timing of occurrence of life cycle event in the in the life cycle of the organism, means timing of occurrence of biological event in the life cycle of an organism in response to abiotic factor. Abiotic factor is a temperature or daylight. So some you must have heard certain crop flower early, certain crop flower late, or certain crop emerge early or mature early. Likewise, vegetation also, certain vegetation is photoperiod sensitive, temperature sensitive, certain vegetation require flowering or blooming, like apple, require very chilling temperature, chilling unit requirement is very high for the apple. So all those, because of this temperature limitation or some photoperiodic limitation, its emergence and also senescence, maturity, as well as flowering and peak growth stage, all influenced by certain these meteorological or environmental parameters. So if we detect, it is possible with meteorological variable, but apart from that, now it is possible to derive where three stages, at least three stages like emergence, start of greenness, peak greenness, and end of growing season, means start of senescence. These three stages at least it can be derived nowadays from the remote sensing with the kind of daily repeat cycle satellite data available from different sources, whether Modi, Spot, AVCHR, or also other sweeps. All the different kind of data is being used to derive phenomenology. Surface meteorology nowadays to certain possible with the geostationary satellite data as well as certain polar orbiting satellite data, where we can get radiation from inset of some UHR data, yeah, meteor second generation satellite data, and temperature also to certain extent we derive from the it's a 3D or vertical profile of temperature, sounder, humidity also to a certain extent we can derive. Leaf area index, fraction, FR. It is very much established product with the Earth resource imaging satellite, NOAA, Nature, or global products are available nowadays for the leaf area index. Leaf area index is nothing but it is the area, leaf area per the ground area, total leaf area per ground area. Fraction of absorbed photosynthetic active radiation means it is how much amount of photosynthetically active radiation being absorbed by the canopy for the photosynthetic process. Because depending upon the crop type, crop geometry, or certain gap fraction in the canopy. If canopy is very sparse, it has got less FFR, fractional or absorb photosynthetic radiation. If canopy is dense, it has ability to absorb most of the PFR, so it has got more FR. Then environmental constant like soil moisture, nutrient, and water all affect the photosynthetic efficiency. So all this soil moisture, water stress, evapotranspiration, as well as nutrient deficiency, to certain extent derived directly from the satellite observation, either multispectral remote sensing or hyperspectral remote sensing. So these are the certain LA and FR product which you can find global database available like MODIS or MISR, multi-angle imaging spectroradiometer, or spot VGT. These are global mission, which are data product freely available from different sites. And it is a mainly different composite 8-day FR is available, 8-day LAI almost for 20 years. Now this MODIS based LAI available FR for different modeling purpose, for biogeochemical modeling. It can be available from the LANDARC NASA site for almost 20 years. So how you can do this? Yesterday I have shown this. So it is mainly light use efficiency, where light use efficiency you can derive from the hyperspectral remote sensing, or you can derive directly by constraining with the environmental stress scalar from the remote sensing data. FFR, different products level, you can, now we have got gain experience to derive this FFR from the satellite remote sensing with the high repeat cycle, whether it is a Indian remote sensing or globally freely available data product, one can use directly into a model. For solar radiation data is now available for most deck in the SEC, inset VHR data. For this inset, solar radiation you can convert into PAR. Then also globally also this PAR data is available. If even those satellite data are not there, one can estimate this kind of PAR observed directly from the meteorological formulae based on temperature or sunshine. Sunshine hours or temperature data can be converted into a PAR from the weather observatory also. So there are different kind of models. If we go into models, because now we have understand which are the different kind of theory approaches are there. But globally implemented models are there, and global database products are available at CASA. 1 degree by 1 degree on monthly time scale globally, NPP database as a function of most of the model. These are light efficiency model. So they have common parameter is the solar radiation, FR, and the water stress and light efficiency. Maybe stress scalar may be derived from different, either from meteorological data or directly from satellite data. So global PM, which is one of the most oldest model, which was implemented to the AVHR data, it was very high resolution radiometer. So 8 by 8 kilometer data from 1981 to almost 30 years database of this NPP database available on 10-day basis from this GPP as a function of same FR, radiation, soil water, and water vapor pressure deficit. And also some model takes into account CO2 also, like SDM, simple diagnostic biospherometric model, It is taking into account CO2 concentration also. Now, recently with the Modi's data, VPM, vegetation photosynthesis model, which is run on a 8 by 8 kilometer, means 8-day basis on a 1 by 1 kilometer data. So you can get GPP database for these 20 to 25, 20 years from certain one site, from website for download. 8 kilometer GPP database available, which you can use directly for validating with or certain carbon budgeting exercise. So it is a vegetation model. Why it is a most important characteristic of BPM model is that it is standalone on satellite observation. It doesn't require any meteorological observation for the stress scalar. It is calculating water stress scalar directly from satellite data based on the land surface vegetation index. But other model, CASA and global PPM, they require meteorological observation with a temperature, precipitation, or vapor pressure deficit to compute water stress scalar. So earlier, okay, when there was no database, particularly if you people who may have question, we have okay India with the 75, 60, 74 very huge land mass, 70% of population depend on agriculture, and we have okay very high, so almost 160 million hectare is under net zone area agriculture, and agriculture contribute also almost 18% of the total greenhouse gas emission from India. It's contributed by the agriculture. So we cannot ignore agriculture of cropland, although okay, it doesn't have much capability to sequester carbon. But if they adopt certain kind of new technology like no tillage or effective irrigation management, or you can say these cover crops in between appropriate crop rotation system, then we surely improve carbon sequestration and we can nullify this emission which contributed by the agriculture. So NPP can also possibly derive directly from the crop statistic data. There is a okay at the district level, Department of Agriculture and Farmer Welfare, they release bulletin statistic at a glance, district level, crop area, production and yield. This yield estimate one can convert into a NPP by taking into account of harvest index and the moisture constant. So it can be converted into an NPP at district level or state level, and that can be used also to compute GPP and other things. Then also this can be one of the most useful source for the validating ecosystem model. So you see here, particularly light efficiency model for Haryana, that okay, wheat area, suppose I want to compute for only wheat, then wheat crop during Rabi season, wheat and sugarcane is there and mustard is there in Haryana. So we have identified wheat, sugarcane and wheat, mustard and other vegetation. Then wheat crop you can extract from the whole classified image. Then corresponding NDVI, that's in particular 8-day Modi's NDVI, then corresponding PAR data. Here, okay, this is what we have estimated PAR data from the Bisto-Campbell equation. For sunshine recorder, you can use also sunshine hour, and based on external spot, you can develop this kind of PAR database. PAR you multiply with the FPAR. FPAR based on ground measurement of FPAR and relating with the NDVI. You can develop a relationship, local specific relationship to obtain the FPAR. Then FPAR you multiply with the PAR, you can get absorb PAR. Absorb PAR you multiply with the light efficiency. Here light efficiency is obtained by down regulating with the water stress scalar and temperature stress scalar. So here you see this water stress scalar we have computed from the vegetation temperature condition index, water deficit index, as well as land surface wetness index from the satellite data, short wave infrared band as well as thermal infrared band. and then it is used to compute light usage efficiency. Finally, multiplying this light usage efficiency and PAR, you can get NPP, gram carbon per meter square per 8 day in Haryana for the wheat crop. It is some sort of validation with the district level crop statistic converted into a NPP. So that is about simple estimation with the light efficiency model. But over the period of time, there is a development going on with respect to the development of satellite, new imaging sensor, new techniques, and new approaches of our algorithm that support improving accuracy of the ecosystem model for the NPP or GPP estimation. So particularly with respect to meteorological input, because most all this model, what I have shown you, it requires solar radiation, insolation database. So earlier insolation database either we were taking from meteorology, or India, we have hardly 20 or 25 stations of solar radiation in India. That cannot be representative of even one district level. So instead of that, if we use certain geostationary based satellite data based solar radiation, like VHR, insect VHR data, or meteor second generation Savary data, so many solar radiation estimation is done with from the satellite data. So that solar radiation is a key driving variable. So if you obtain from the high resolution, partial and temporal resolution meteorological input, then it can improve the accuracy of this GPP model. Then incorporate fraction of crop species, because particularly with the agricultural land mass, there are different crops like rice, wheat, or pulses. These are all crops are C3 crops. They have different kind of photosynthetic pathway. They don't have very high water efficiency, but they are highly responsive to the CO2 concentration. They are not having high light usage efficiency, but C4 crops are there, like sugarcane, maize, sorghum, which are C4 crops, which are got high biomass, high photosynthetic efficiency, low compensation point, so they can have more optimum temperature for C4 crops is almost 35 to 40 degree compared to wheat. It is I have shown you 30 degree, maybe or less than 30 degree, 25 to 30 degree for the wheat or other C3 crops. For C4 crops, it is always 35 and above. They sustain even very high temperature. That is why we need to take into account C3 and C4 crops into terrestrial ecosystem model for regulating or light usage efficiency quotient. So maximum light usage efficiency one can take, because as I say, there is a strengthening of the flux tower network. This maximum light usage efficiency as a quotient, we can directly take from the different flux tower measurement carried out at over different biome specific. Now it is possible. Earlier we used to take only one single measurement for the deciduous forest or particular evergreen forest or C3 crops or C4 crops. Now crop specific or particular forest type specific. If we have flux tower observation, we can derive maximum light efficiency and use as an input to the model. Apart from that, now UAV is there and hyperspectral imaging is evolving. This has got different kind of indices like photochemical reflectance index. This is highly sensitive to the photosynthetic efficiency, and that can be used for the further upscaling. Then environmental stress scalar also, particular sphere and TR region, that can be exploited. Different kind of water stress indices can be derived and tested to estimate environmental water stress. So this is a flow chart of vegetation photosynthesis model, where from ED core whereas flux tower directly light usage efficiency EG that goes, then FFR that derived from the satellite with the certain prospect cell model inversion. PAR from this you can derive either from satellite or from ground weather observatory. Water stress scalar from LSWI, that from Modi's data, EVI also from Modi's data, and then finally Modi's or spot vegetation, climatic data you require. So VPM model does not need any soil water model. As I said, it doesn't. It standalone based on the solely on satellite observation. It doesn't require any weather-based information like temperature or precipitation to run the soil water balance model. So it is largely applicable with the given by satellite data and serve as an independent diagnostic tool. So this is one VPM model what we have earlier applied with the spot vegetation data in 2003. Now you see whole India, that cropland with taking into account the C3, C4 fraction also. We could estimate water stress from the LSWI, temperature stress scalar, FFR, and this NDVI, EVI from FFR from NDVI, PAR from the cloud-based relationship with the Modi's. And finally, we could able to estimate crop NPP. Now here you see crop NPP in Indian landmass, it is around 0.859 pentagram carbon. But GPP is a 1.3 pentagram carbon in India. And if you see the different kind of cropping system, so sugarcane wheat system, which is practiced mainly in the western UP, has the highest duration. Yesterday, as I showed, we need to identify for the monitoring of the ecosystem exchange over CO2 and carbon methane exchange, both strength, intensity, and duration of the sink and source. So this sugarcane wheat system, which has got the highest duration of the GPP duration with the higher GPP, and also rice wheat system, which has got two peak, that, and then also cotton and wheat. So we can derive on a temporal pattern of the different cropping system, and it can be also validated with the statistical based crop NPP against the VPM based NPP and CASA NPP. Now you see there is a close relation we could obtain for the crop NPP or GPP fluxes obtained from the satellite data. Same VPM model, side scale for the galvanic flux tower division for 3 years. Okay, we could be able to do with the Landsat data also on monthly time scale, high resolution GPP, but it cannot be possible to derive for whole India. So if it is a small study for upscaling purpose, we can test VPM kind of model for the divisional scale forest GPP or fluxes evaluation. Similarly, for the barcode forest also tested different kind of TG model or light efficiency model, all tested with the along with the Modi's algorithm also. Now you see here that particularly remote sensing, regional specific parameterization. If we parameterize this light efficiency model with the light efficiency constant or the temperature, optimum temperature from the and flux tower base light efficiency, then it improves the agreement. So here you see RS LUE based remote sensing driven LUE models that gives the highest agreement with the flux tower observation of the GPP. But last you can see Modi's 17, Modi's algorithm, which is freely publicly available data product available on GPP. It is very highly underestimating, almost one third to 1/4 estimation is there of the actual observation. So what I want to convey to all of you that there are so many databases available, publicly free GPP carbon fluxes product and databases available. So all those databases we need to look into about uncertainty, how good they hold for the particular region or particular nation to evaluate carbon balance. Because this says, as I shown here, Modi's not only for barcode forest site, other site also, your that cropland site also, it is underestimating as a 1/3 to 1/4 of the observed tower based NP. So those Modi's based database is not at all suitable to estimate carbon fluxes or developing certain kind of ecosystem services. So we have to parameterize, regionally calibrate our own ecosystem model, and then apply to derive carbon budget or carbon fluxes for our country and a region. So this is one model which we have parameterized for India CASA model, parameterized for the different biome specific type and made it implemented on a national level at the grid scale of 8 by 8 kilometer for 25 years. So CASA model that takes into account radiation, vegetation index database from the remote sensing, that is a Carnage and Stanford approach. It was implemented with the Modi's as well as spot vegetation data for the generating carbon fluxes of NPP, net ecosystem productivity, and the soil organic carbon. So here you see this is initially for this. I have shown you for VPM, it is a 1.34 pentagram carbon for the cropland. But here for the whole forest and crop and all other land use, it is 1.6 pentagram carbon. But cropland, you see, 0.895 from CASA, but we got for the same year 0.859. Means hardly there is much difference. So this is both spot registration database with the VPM or this CASA. Both are working well for the estimating crop NPP from satellite. Then you see this is all different vegetation type wise, CASA, CFIX and MODIS based contribution to total national NPP budget. So this is one publication is there. So particularly the deciduous, this evergreen forest and these those are having very high value of NPP. 9 evergreen broadleaf forest that has got the highest 989, followed by this another forest that is a deciduous broadleaf forest. But cropland equally that is having a 898. It managed cropland in Indo-Gangetic plain that contribute significantly in the crop NPP of the India. So this is all about some statistic and internal variability is also there. Indo-Gangetic plain that is contributing very high cropland NPP. Peninsular India which has got less than 31 gram carbon per month. This is LPP gram carbon per gram carbon per meter square per month. That is, so it has got very less than 21 almost throughout up to 2005. But Indo-Gangetic plain, if you see, it is almost more than 35 throughout 25 years. So that is what I want to say, so that Indo-Gangetic plain, cropland, it is very high biomass crops are there and very high cropping intensity. As a result, it is generating high NPP and finally the carbon input to the soil. So both, that is climatic control, both NPP, particularly in India, that is directly related with the precipitation, because our country is a tropical countries. So in our country, precipitation has the dominant control on the vegetation greenness. So any primary productivity or crop productivity, that is directly related with the precipitation. That is why we are getting the, for irrigated cropland also precipitation 0.49, very good correlation, but non-irrigated, which has got very high correlation 0.65. That means we are in semi-arid country or dominantly arid to sub-humid, semi-arid and sub-humid countries. So we got more area under the rain and dry land crops. So we are having a dominant control by precipitation. So precipitation mainly regulate the interannual variability in the primary net carbon input or net carbon productivity. NEP, that is nothing but the net ecosystem exchange of vegetation and the atmosphere. How much carbon is exchanged between the biosphere and the atmosphere. That means between vegetation, different kind of terrestrial ecosystem in India and the atmosphere. So here you see wherever negative is there, you can say that is a Negative NEP, wherever you find negative NEP, that means it is a source. Positive NEP means it is a mainly higher productivity of it is a sink. NEP positive means sink. It is different from the sign convention is there. Minus NE equal to NEP. So if net ecosystem exchange is negative, then you can say it is a source. And if it net ecosystem exchange is positive, then you can say it is sink. But it is a negative sign. Sign convention is negative. So we have NEP is a positive means sink and negative means source. So here you can see different area. Whenever there is a drought, early part of the 1980 century, or 1981 to 87 almost, series of droughts were there. As a result, there was large scale decline in the productivity, and finally country was mainly under source. But over the period of some year were under sink and some year were source, depending upon the how rainfall condition and drought effect. So different kind of data you can use for the amplitude. You can compute NDVI, semi-annual. So Modis and IIRS, both are okay, almost good database, but they are giving a different kind of signal about the semi amplitude as well as this NPP data. Now here you see Modi's NPP budget is higher than IIRS budget. Why? By 25%, because IIRS data is a coarse resolution data, 8 kilometer. Modi's NPP, Modi's data is a 1 kilometer. So because of coarse resolution, its averaging effect will be there. As a result, it is going to decline. NPP is declining by 25% compared to Modi's. That is why here scale is very much important, or resolution is very much important. If you use very coarse resolution data, then your final carbon budget will be lower down. Means finally input sink will goes down. But if you have coarse high resolution data, accurate data what required, then you will get correct. So NEP budget always for Modi's NEP budget always for Modi's is positive, but for IIRS it is either negative or positive because of its coarse resolution in nature. Because coarse resolution data cannot resolve the vegetation and other environmental condition more effectively. Representativeness means representativeness of the climate regime and the vegetation ginness, which is influenced by climate regime, cannot be resolved effectively compared to the Modi's, which is a very good, okay, comparatively good resolution satellite data. So here CASA model for regional versus global, also there is a large degree of variability is there, 50 against 20 teragram carbon. Regional CASA NEP with Modi's NDVI and simulation, and global CASA NEP. So global, if we do global, it is having okay different value of NEP. But if we are using only for the regional with our own parameterization of the CASA model, then value of NEP is different. That is what I highlight here is that we had to do regional parameterization of the any ecosystem model which we can use for the simulation of climate fluxes. So inverse here actually mainly it is mainly how atmospheric growth rate is going to happen, but mainly El Nino years. Wherever there is a El Nino or drought years is there, NEP goes down, means more source is there. Wherever La Nina years is there, they are mainly the sink. But in India, NEP budget, it is not directly okay controlling the increasing rate of the CO2. CO2 variability is not directly linked with the NEP budget because we are tropical countries. So there are different kind of processes that affect the release of CO2 to the atmosphere, like forest fire, tropical deforestation, land use change, or also harvest, crop harvest. All is affecting the finally your this CO2 growth of growth rate of CO2. So unless we do not take into account that disturbance design, NEP disturbance design, how much contribution of disturbance design, harvest, forest fire, deforestation, we cannot define accurately the what is the contribution of this carbon budget to the increasing CO2 growth rate. That is NBP. Unless we do not go up to net biomass productivity, we cannot directly link that budget, carbon budget exercise with directly CO2 increasing rate. So there are certain process-based model also is there, like one of the most common model is BioBGC. They are also mainly the meteorology driven, climate driven, which requires certain ecophysiological parameter. It can be run for the with the meteorological data set. So after defining crop parameter, site-specific data. So you see that for different eucalyptus, mixed plantation, poplar, and teak, different kind of forest site, we could able to simulate annual NPP for the different plantation. But this NPP is very low compared to the what simulated with the satellite observation. So you can do also for monthly time scale, okay, NEP, gross primary productivity, heterotrophic respiration, and ecosystem respiration directly from the BioBGC. And it can be tested for the different forest type site to evaluate whether it works. But it can work only, you see also one validation model with the measure GPP. It works because why GPP is giving it is correct, but NEP and heterotrophic respiration, it is not giving correct. Because that is a almost model is a overestimating compared to the this observation. Why? Because model is here, okay, it's a model is more negative in case of NEI, uptake is model more, and then ecosystem respiration also, you can see model is more. So they are overestimating because here we could not parameterize all parameter which is obtained from the flux tower data. We could, if you parameterize like all parameter like okay, temperature sensitivity, coefficient of respiration, light usage efficiency coefficient from flux tower, then you can get the better estimate. So here, okay, GPP we are getting correct because we could able to parameterize light usage efficiency that Emax directly from the flux tower for the mixed plantation site. So it is giving correct simulation. So machine, another approach, as I said, process-based model, efficiency, process-based, and then there is a machine learning. Machine learning based. So machine learning based or dynamic vegetation model. In dynamic vegetation model, there are different kind of tools, then tree feed, then there is also a model like LPJ, Luna Post Jena model, which are mainly able to simulate different structure and composition of the biomes. Machine learning that applies with the support vector machine or random forest or AI artificial neural network with the observation side. But one challenging thing in the case of machine learning based approach is that we need to have optimum and adequate number of training sites. Right now in India, we have hardly 20 sites of flux tower observation. So we cannot generate this kind of map, what I am showing. This is what globally there are almost 900 sites. Satellites are, there is no lack of information available from satellite. Depth of satellite observation are freely available. So you can directly use satellite observation of LI, FFR, land surface temperature, soil moisture, different kind of thing directly linked with the observation, and you can develop this kind of partially explicit field of GPP, NE, and terrestrial ecosystem respiration. So, but on the right side, there is a same dynamic global vegetation model, which are run on the half-degree grid scale. You are seeing, okay, overall response is okay, but best accurate is a machine learning based because they are based on the observation itself. Global dynamic global vegetation model, they doesn't take into account satellite observation. They are mainly climate driven model. So whatever parameterization, if you do good parameterization of the lens, different biogeochemical processes, within the model, you can have better accuracy. If you don't do some biome-specific parameterization for a region you are simulating, it may give you a errorness. It is like a black box. Unless you don't do regional calibration and parameterization of this kind of model, they don't work. So fourth approach is a sun-induced fluorescence. Sun-induced fluorescence based photosynthesis is very much key, vital, because nowadays sun-induced fluorescence means it is a competitive energy with the reflective. It is a weak emitted energy from the chloroplast reaction center. Once photosynthetically active radiation impinging on the canopy surface, some part of it is absorbed by the canopy. But all this absorbed part is not being utilized in the photosynthesis. Some part is being emitted or dissipated as a heat from the chloroplast reaction center. Here you see chlorophyll fluorescence. It is a 0.5 to only 2%. Here you see absorption, whatever part which is absorbed by the chloroplast reaction center, which is useful in the photosynthesis for almost up to 82%. But heat, some part is distributed as a heat also. But so here fluorescence is a very weak signal. So if you want to monitor or detect this weak energy signal emitted from the chloroplast reaction center, then you need to have a very narrow band width. That is from far infrared like 0.74 to 0.78, or it is also for red 0.63 to 0.68. There some signal you will get about fluorescence. So here you see red 6.5 to this, there is a signal, and here 740 wavelength, 740 nanometer and 685 nanometer. You can see the peak signal of the fluorescence. So that so you can detect this weak energy emitted as a fluorescence. So how you can evaluate? This is fluorescence signal. Like here. What I have said, two signal, red and red. We derive. This is inflection point, and this is a absorption. So this inflection point. You derive this fluorescence signal. Very limited signal is there. From observation side, from the this at the field level or at the landscape level, you can use once optical sensor like fluorometer. With the fluorometer, you see high resolution, very high frequency or high resolution. You can get fluorometer leaf level sun-induced fluorescence. Then next level is with a UAV. You can get some sensor on at the 714 nanometer wavelength and 680 nanometer, 545 nanometer wavelength. You can get that signal of sun-induced fluorescence with the UAV-based camera. Third is the spaceborne airborne sensor. Take aerial flight with the sun-induced fluorescence sensor. You can measure also at the landscape level. Fourth is the spaceborne sensor that is also available nowadays at the global scale or regional scale. So different kind of sun-induced fluorescence measurement is available nowadays from the flex, that is very recent. Fluorescence sensor is there, launched by the European Space Agency. We could able to get fluorescence very accurately at very high resolution level. Then there are different sensors like GO2, METOP, and there is a GOSET. This is also GOSET, and then OCO2, then TROPOMI. These all new sensor which are providing global scale sun-induced fluorescence measurement, which is directly linked to the photosynthesis. So this is a global map of sun-induced fluorescence from the global ozone monitoring experiment satellite. So this sun-induced fluorescence that is nowadays, it has got tremendous potential for crop monitoring also. So space-based crop monitoring is key to food security. So mostly light use efficiency based models are used for the estimating agriculture productivity. But nowadays, with the sun-induced fluorescence available, it can be directly linked with the gross photosynthesis, and we can derive better estimate of the crop productivity. So various, okay, India, it is not still gearing up, but all other countries, sun-induced fluorescence technique has been widely used for the ground, airborne, as well as space-based observation studies across Australia, China, and all other countries. India, now we are gearing to use sun-induced fluorescence for the photosynthesis. Like, okay, sun-induced fluorescence, like LU model, same. Yeah, but okay, sun-induced fluorescence converted into a efficiency. Then finally, we will get C3, C4 for correction. Then carbon use efficiency we can compute as a ratio of GPP, NEP, and then finally harvest index. That okay, already I saw crop statistic converted into NPP, and then to GPP you can validate. So finally, this flux tower based GPP. Along with this statistical approach, all can be used to derive the photosynthesis process. Here you see that crop statistic we have converted in for indocandidate plant for the crop NPP and related with the sun-induced fluorescence. For different years, you see very good relationship we could obtain comparatively better than the vegetation index derived from the satellite. So sun-induced fluorescence, it is working well to derive link with the gross photosynthesis or net primary productivity or cropland also. So now overall summary or overview of different kind of modeling exercise, if we look it. So initially there was a Miami model, as I said earlier, temperature or precipitation based, simple relationship between NPP against temperature and precipitation. Then came 1980s, there is a trace transport model. Then NDVI into productivity, that's Goa 1985, simple relationship between NDVI and the NPP. Then came also physiology into global land model, Seller, SIPS 2, 1990s, SIP, SWOT vegetation scheme, that is a mainly climate driven model, physiology based. So 1997 it has came into existence. Then after okay, almost 2004 or even 90s, there was a global PM model. Then okay, light use efficiency based Modi's GPP algorithm came in the first part of the early part of the current century. That LU based model. Then machine learning. Now 2010 onwards, machine learning because of very updatation of the flux tower observation network across globe. Every country is now setting up their own network of like IndoFlux. India is doing for IndoFlux measurement network, China Flux or Asia Flux, all are growing. So more and more observation sites are available. So and more good dearth of information or advanced satellite of sensors are being developed which provide information on sun-induced fluorescence, hyperspectral sensors, and also solar radiation or meteorological database directly from satellites. All can be integrated with this satellite observation through certain machine learning algorithm to derive GPP. So then, okay, this okay, you can after machine learning with the remotely sensed indices or remotely sensed variable. Latest one is a in current last 4-5 years, large scale development is that sun-induced fluorescence based GPP. Now, gross primary productivity and carbon fluxes are estimated directly from the sun-induced fluorescence by inversion of CO2 along with the SIF obtained from the satellite. So here you see different kind of techniques. Okay, what as I said in general, right now NPP is our GPP is around 120 to 123 pentagram carbon per year, whole global. Now you see here machine learning base. that black, this round black circle, that is giving almost 120 throughout 20 years accurately. But here you see this is particularly this the other model. So mainly that machine learning based and SIR based fluorescence or light efficiency based model is underestimating in current situation. If you see, it is grossly underestimating, less than 100 pentagram carbon it is giving. But machine learning techniques, it is giving quite accurate, comparable with the certain process based model. So then climatic control also, climate, like we are in the arid countries, so we must worried about even we are strengthening afforestation program or different kind of good high biomass variety or carbon input with the better irrigation management, fertilizer management in the cropland system. All effort are going on, but at the same time climate is regulating the carbon fluxes. If there are more drought, precipitation control on NPP and the soil moisture control and temperature control on the respiration. So both, if you see here from the slide, red or orange means it is a temperature control, blue means precipitation control. So you see in India mainly it is a precipitation control ecosystem functioning is there. Precipitation mainly control the both terrestrial ecosystem respiration as well as GPP. But to certain extent, if you see that in GPP, some this Eastern India or we are finding little bit control of temperature also. So significant correlation we are seeing mainly for whole Indian ecosystem with the precipitation for the both GPP as well as terrestrial ecosystem respiration. So precipitation, if droughts are there, our ecosystem easily transits from sink to the source. And we are already in tropical countries. There is a large degree of variability in the drought events and all those things is that recurrent last 4 or 5 years. If you see, recurrent droughts are happening. So despite our tremendous effort of afforestation or increasing terrestrial sink by some government efforts is there, there is some kind of drought events which are negating our effort also to certain extent for Indian ecosystem. So if we have to being a carbon sink for the year to come and contribute more towards terrestrial carbon sequestration or terrestrial sink and reducing the target of carbon emission by the fossil fuel. Because we cannot compromise the development agenda, but at the same time, if we contribute to improving the carbon sequestration to terrestrial sink capacity, then surely with the whatever kind of climate or other control is there, we keep effort of more and more greenery, more and more afforestation program or effective integrated nutrient and water management, zero tilling, organic farming, all can help to derive more appropriate carbon budget to reduce more dependence on reducing fossil fuel emission. So this is all about upscaling and modeling. More detail about so vegetation carbon pool assessment and asset, because I had talked mainly on the observational network, role of Earth observation, and mainly the primary carbon fluxes, measurement of ecosystem exchange. That is all related to fluxes or exchange. But static stock, how much there is a store reservoir is there. What is the stock of the vegetation carbon stock or soil carbon stock? How it can be possibly derived from the remote sensing will be talked in the later lecture. Thank you all.